this video, we're going to talk about finding solutions to non-homogeneous systems of equations. So as a quick reminder, what a homogeneous system of equations means is that everything is set equal to 0. A non-homogeneous system of equations is set equal to some other vector b that's not the 0 vector. If you write it out as a system, you're going to see the first equation equal to some number, the second equation equal to some number, and at least one of those numbers needs to be non-zero. So remember, the set of solutions to the null equation, ax equals 0, that's a homogeneous system, is the null space. That's the definition of the null space. It's the vector space consisting of all those vectors x that solve the equation ax equals 0. So this is a vector space. It's closed under addition, it's closed under scalar multiplication, and it contains the 0 vector. The natural question to ask is, what about the solutions to ax equals b? If the solutions to ax equals 0 form a vector space, what about the solutions to some generic system of equations, ax equals b? Is this a vector subspace? And well, the answer to that is no, it's not. It's not closed under addition, scalar multiplication, and it doesn't contain the 0 vector. And let's see why that's the case. Suppose you have two solutions that you want to add together, x and y. If x is a solution, then ax is equal to b. And if y is a solution, then ay is equal to b. But ax plus y is equal to ax plus ay, and now that's equal to 2b, not b. So that's not a solution. Likewise, if you have x and it's a solution, ax equals b, and then you take a scalar multiple, a of a scalar times x is a scalar times ax. And that's going to be a scalar multiple of b. So unless c is equal to 1, this isn't going to work out either. And also, because 0 solves the null equation, a 0 vector is equal to 0 vector, 0 is not in the set of solutions to ax equals b either, because it's not giving us ax equals b. So it fails on all fronts. So since it's not a vector subspace, we can't write down a basis in order to describe the set of solutions to ax equals b. So how do we describe that set of solutions? Well, fortunately, the answer to this question, how to describe generic solutions to ax equals b, is given to us by the following theorem statement. What you do is you find one particular solution. That's called xp. And if you have this particular solution that solves ax equals b, then all of the other solutions that are out there can be written as the particular solution plus something that solves the null equation. That's xh. So xp solves ax equals b, but xh doesn't solve ax equals b, it solves ax equals 0. Let's write down a proof of this theorem. It's super short. Well, let's start by checking that something of the form xp plus xh really is a solution. If you take x, and it's of the form x particular plus something that solves ax equals 0, then ax is equal to a xp plus xh, and that's equal to axp plus axh. And axp gives us b, and axh gives us 0 when we multiply by a, and that's equal to b. So certainly this vector x equal to xp plus h, this is a solution. We just checked that. Now, why is any other vector that solves the equation of this form? Suppose y is any other solution. Since y is a solution and xp is a particular solution, we have that ay is equal to b and axp is also equal to b. So that means we can take their difference and get the 0 vector. 0 is b minus b, and that's ay minus axp, which is the same thing as a times the vector y minus xp. But see, now what this tells us is that this vector y minus xp, this is some vector that has to belong to the null space, because this vector is solving a times that vector equals the 0 vector. So because it's in the null space, that means it's some vector of the form xh. So we may as well call this vector right here xh. But now what we have is that y minus xp is equal to xh for some vector xh in the null space. But that, of course, just tells us that y is of the form xp plus xh, just as we wanted to show. Any vector that solves ax equals b can be found in this way. You find a particular solution, and then you modify it by anything in the null space. that gives you a general description of solutions to the non-homogeneous linear system AX equals B. It would be good now for us to do an example of this. So for this example, we're going to describe the set of all solutions to AX equals B when A is the specific matrix that you see here, and B is the vector 5 minus 7, 0. So step 1 is going to be to find a particular solution. Now I've made this example so that it's pretty easy, and in particular this matrix that we're looking at, it's already in reduced form. If you had any old matrix, you'd first want to put it into reduced row echelon form, but we've done that calculation a lot of times, so I didn't want to have to go through all the row operations. So let's start with something that's already a pretty simple matrix. Now we want to find a solution to the system of equations AX equals B, which means, use Gaussian elimination, put it in reduced row echelon form, and then solve. The system that goes along with this matrix, by the way, if you like looking at it as a system, is this one. Taking the coefficients of the matrix and putting them back into a system of equations. We see that we have a couple of free variables. x3 and x4 can be anything, but once you set x3 and x4 to be something, then that tells you what x2 has to be, and it also tells you what x1 has to be from this equation. x1 and x2 are determined by these equations right here. It's important to remember that when you have free variables, you have to name them, and that's something that I've done here. My two free variables are x3 and x4, and so I've given them special names. x3 is going to be some number s, and x4 is some number t. And that's why when I write out what x1 is, I see an s and a t in the equation. That's normally where I would see my x3 and my x4, but I've called them s and t here. And likewise, my x2 is given by minus 7 and then minus x3 plus 3x4 from this equation, but I've named my x3 and my x4 variables with s and t here. Now I want to unpack this solution and put it into vector notation. So the vector that describes the same thing as what's written here is 5 minus 2s minus t for x1, that comes from here, minus 7 minus s plus 3t, that comes from s2, which is given here, and then x3 and x4. Those were my free variables, so I just named them s and I named them t. And now s and t can be any real numbers. So this is a perfectly fine way to describe your solutions to the system of equations. But I would like to rewrite this so that it's clear that this itself is of the form x particular plus something in the null space. So I can break this vector into a sum of 3 vectors. And what I'm going to do is I'm going to take the pieces that are in front of s, the pieces that are in front of t, and then the pieces that aren't in front of anything. So my vector is also the sum of the 3 vectors 5 minus 7, 0, 0. So I'm taking the constant terms here that aren't in front of s or t. And then this is added to the s parts. So 2s minus s, s, and then there's no s in the last coordinate there. And then let me take the t parts. Minus t, 3t, 0, and t. And then let me do one more step, and then let me take the s's and bring them on the outside, and take the t's and bring them on the outside as if they were scalars. And when I do that, I see 5 minus 7, 0, 0. And then I'm going to have plus s, and then the vector 2 minus 1, 1, 0, plus t times the vector minus 1, 3, 0, 1. I have now my solution, my general solution, which describes any solution to the system of equations the way we'd done it before, written as 3 vectors added together. And what we're staring at when we look at it this way is exactly that description, xp plus xh. This part right here, this is our x particular, xp for particular. This is the particular solution when you have set s equals 0 and t equals 0. This is no longer a generic solution, but it's literally just the vector 5 minus 7, 0, 0. And if you plug that into the system of equations here, you're going to get a solution. So there's our particular solution. And then the second 2 vectors added together, this is a generic vector in the null space. This is our xh. And if you take this and take the system of equations, ax equals 0, then any of the vectors described by what is given here in purple is going to solve ax equals 0. That system means take this, but have it all set equal to 0 instead of equal to 5 and minus 7. So here's our homogeneous system that goes along with this 0, 0, 0. And now if you take something of the form s times 2 minus 1, 1, 0 plus t times minus 1, 3, 0, 1, and you plug it into here, you're going to get a solution. Let's check one just to be sure. When s and t are both equal to 1, that would give us these two vectors added together. So that would give us the vector 2 minus 1, 1, 0 plus minus 1, 3, 0, 1, which if I add correctly is 1, 2, 1, 1. And now this ought to solve my system of equations. 1 minus 2 plus 1 is equal to 0. Check. 2 plus 1 minus 3 is equal to 0. Check, and then 0 is equal to 0. So it does solve the system of equations. So when we decompose it this way, we see that we really do have something of the form that's described in that theorem. I want to make one more observation about this example, and that's that when you write down a basis for the null space, it's this same set of vectors that you see here. So let's take our matrix A. Let's do this on the next page. Okay, let's practice writing down a basis for the null space of A. We're going to see we get the exact same expressions that we have here. So if the question that I had asked you to solve was, give me a basis for the null space of A. Remember, a basis for the null space of A means we're trying to describe the null equation Ax equals 0. What we would do is we would take our reduced row echelon form of the matrix, which fortunately is already like that. The ones that I've highlighted here in blue are independent column vectors, and then these last two ones are dependent. So for each of these two dependent vectors, I would have a linear dependence relation that would give me the basis vector for the null space. I can see from here that column 3 is equal to minus 2 times column 1 plus column 2. And then I can also see that column 4 is equal to 1 times column 1 minus 3 times column 2. Those are the two dependency relations that I see from here and from here. Now this one I can rewrite as 0 is equal to minus 2 column 1 plus 1 column 2 minus 1 column 3 plus 0 column 4, which didn't factor into it. And this one I can rewrite as 0 is equal to 1 column 1 minus 3 column 2 plus 0 column 3 minus 1 column 4. And out of these two expressions, when I pick off the coefficients and put them into a vector, let's look at the two vectors that I get. In the first case, I'm going to get minus 2, 1, minus 1, 0. And in the second case, I'm going to get 1, minus 3, 0, minus 1. Let's look back at those two vectors that I saw before when I described my system of equations. It should be the same vectors. And indeed it is. So what I've written here is a generic linear combination. XH means I'm taking any vector in the null space, and that means it should be a linear combination of the basis vectors for the null space. These are my two basis vectors for the null space, and when I take a linear combination of the form s times the first plus t times the second, I'm just describing some old vector in the null space. So here we have the kind of description that we get when we solve a problem that says ask for a basis for the null space. And in the previous way of looking at this problem, we were trying to describe the set of solutions to a non-homogeneous equation, and we see it showing up there as well.